All right, so this particular pre-lecture is going to talk about a concept called degree of freedom analysis. And the purpose of a degree of freedom analysis is to help us determine whether or not there's actually enough information to solve a problem. So believe it or not, sometimes problems are underspecified, we don't have enough information, and this happens a lot in the real world. And this can happen in a mass and energy balance as well, because we might not have enough information in order to solve. Sometimes we actually have more than enough information, and the idea of a degree of freedom analysis is to tell us what state we're in. So generally, when it comes to a degree of freedom analysis, the way that we perform this is we start by drawing and completely labeling a flow diagram. So labeling not only what you know, but what else you also don't know. So draw and completely label it. Then you go through and you count the number of variables. So this is why we've talking about M's and X's and N's and Y's and things like that. That's why we want to care about these variables. We need to go count them. And then we figure out what are the number of independent equations that we have. So you've started to see that when we use the general balance equation, we get different equations that we can write. And some of them are independent of each other and some are not. So that's the general procedure. So when we do a degree of freedom analysis, there are three possibilities that come out of the analysis. The first is that the number of degrees of freedom equals 0. That means there are the same number of independent equations as unknowns, and in principle, the problem can be solved. So what do we want when we have problems? We want 0 degrees of freedom. That means there aren't any extraneous variables or extraneous independent equations floating around. So we want the number of independent equations to equal the number of unknowns, and then we can solve. So it's the same principle that you might have seen in algebra or in different science classes, right? 2 equations, 2 unknowns. That's what this means. We can also have the number of degrees of freedom greater than 0, and that means that there are more unknowns than there are independent equations, and that means that we need at least a certain amount of additional variables, and that number of additional variables that we need is equal to the number of degrees of freedom. So let's say, for example, that we have 3 unknowns. If we only have 2 independent equations, that means we have 1 degree of freedom, which means we need 1 more equation to be specified. The last possibility that we can have is the number of degrees of freedom is less than 0, which means that there's more independent equation than there are unknowns, which means that maybe we incorrectly label something, or this is what's called an overspecified problem. So there's redundant reactions, there's too many things going on. And an overspecified problem is sometimes challenging because it can lead to issues with information not aligning with each other. So these are the 3 outcomes that we can get. So the ideal outcome is that is 0 degrees of freedom. That's what we want. It wouldn't be bad if we had greater than or less than, right? But we'd have to think about how do we get things to work out. So when we write our mass balance equations, we have different sources of equations that we can write to get these independent equations. And the first one is to write those material balances, right? So start with the general balance equation and use the general balance equation to write the overall balance and then a balance on any of the other species in the system. That will give us sources of equations. Now we're not there yet in the semester, but we can also use energy balances as a way to also write balances on a system. We can also use what are called process specifications, and these are relationships between variables, and these are going to get really, really important. So things like if we only have A and B coming into a stream, we know that the fractions of those must equal to 100%. That's a process specification. It's a relationship between X sub A and X sub B in a given stream. That's important, and that's a possible source of an equation. We can also have physical properties and laws. So this is using things like density equals mass over volume, or the relationship between moles and the number of kilograms in a sample by using the molecular weight. So we can use that as a way to help us out. We can also use physical constraints. We don't see this all that much in the very couple beginning equations that we solve, but as we start to get to pressure and temperature and volume and things like that, physical constraints of an actual system come into play a little bit more. And we can also use stoichiometric reactions. We're going to get to the point where generation and consumption do not equal 0 anymore in this class. And using stoichiometry is going to be a way that we can add additional equations to help us solve problems. So last thing that I want to say about kind of the general procedure for solving single unit mass balances is that we're going to have to add in this new concept of degree of freedom analysis. So in general, when we're solving those single unit mass balance calculations, we want to choose a basis of calculation, which is the amount or flow rate of one process stream. Okay, so we always start with a basis of calculation. Then we draw our flow chart, we fill in all the known variables and the unknown variables as well. The unknowns is the important part in this step because that's going to play into degree of freedom analysis. Then we try to express what the problem statement asks for in terms of our labeled variables. Can you circle the thing that you need to solve for? If you're given mass and moles, we want to make sure that everything is in the same basis and everything is in the same unit. So we either want to go all mass or all moles. We don't want to go in between the two, right? That's going to get confusing real fast. So if you're given mass and moles, make sure you pick one to work with. Then we perform our degree of freedom analysis to see if this is actually a solvable problem. From there, we would take all of our equations and we would combine them. We would circle variables to solve for. We would check our solution by doing some kind of a validation method. So any balances you didn't use, that's a way to do back substitution, and that's going to be important going forward. And then we solve for any additional variables using our equations. So this is our general procedure, right? If you get stuck on a problem on an exam or on a homework assessment, this is the set of steps. This is a great slide to have right at the front of your notes with your other equations to say, okay, if I get stuck, did I do each of these steps in order to figure out how to solve this problem? So that's degree of freedom analysis and how it plays into single unit mass balance calculations. We are going to work through an example 4.4 that looks at benzene and toluene mixing, and we're going to add an additional video to that example to explain how to actually do a degree of freedom analysis.